Welcome geniuses, I'm Genie, your best buddy for A-levels. In this channel, we'll bring you to explore the secret formula behind success.
Today we will go into Chapter 5, Chemical Energetics for A2, to learn how to construct a Born-Haber cycle. So we'll make use of this question from October-November 2005, Paper 4, Question 1C, to construct a Born-Haber cycle to calculate a value for the lattice energy of silver bromide. To construct a Born-Haber cycle, we always got to start with enthalpy change of formation and end with lattice energy. So we have to make use of the given information to turn the elements needed for the enthalpy change of formation step by step into the gaseous ions needed for the lattice energy. So we will have y-axis, which is energy. And if the enthalpy change of reaction is an endothermic reaction, arrow will be pointing upward. And if the reaction is an exothermic reaction, the arrow will be pointing downward. So let's start with the enthalpy change of formation of silver bromide. So it is an exothermic reaction, and it is from the element, which is silver solid plus half Br2 liquid with negative 100 kilojoules to form 1 mole of silver bromide solid. So starting with this, we have to make use of the given information, step by step moving into gaseous ions to form 1 mole of silver bromide for the lattice energy. So the very beginning, we will make use of atomization of silver to turn silver solid into silver gas. So we did nothing to Br2, so we just write it back. And for this process to go, it is enthalpy change of atomization of silver, and the energy involved is positive 285 kilojoule per mole. So therefore, the arrow is pointing upward because this is an endothermic reaction. So the next reaction to go is to ionize the silver atom. So where it involves first ionization energy of silver, so where it involves positive 731 kilojoule per mole. So it turns silver gas into silver plus gas with removal of 1 electron. So this is the first ionization energy of silver. So after turning silver into ions, the next to go is to atomize Br2. To turn Br2 into gaseous atom, it involves enthalpy change of atomization of bromine, where the value is positive 112 kilojoules per mole. So it is to turn half Br2 into 1 Br gas, which is in gaseous state. And next to go is to turn Br gas into an anion. So where it is actually the first electron affinity of bromine. So the value is negative 325. So since it is an exothermic reaction, So the arrow will be pointing downward. So it is to turn Br gas into Br minus gas. So these are the gaseous ions we need in lattice energy to form 1 mole of ionic solid. So the arrow will be pointing all the way down to AgBr solid, and it is the lattice energy. So this is a complete Born-Haber cycle to find lattice energy of silver bromide. So in order to have the calculation, so we have to apply Hess law, where the definition of Hess law is that the enthalpy change from reactant to product remain constant or the same regardless to route taken, provided initial and final conditions are the same. So here we could actually see the simple route to turn this Ag solid and half Br to liquid into Ag Br solid. It involves negative 100 kilojoules per mole. So then we could have another route to turn this element all the way into the same AgBr solid, involving more reactions to go, but the enthalpy change will remain the same. So then we could move into the calculation to have this equation. So where it is the route 1 to have AgBr solid, and the route 2 will involve all the way into AgBr solid, but the enthalpy change are the same, provided initial and final condition are the same. So we will sum all of them up. And at last, we have lattice energy. So with this, we could actually get the value of enthalpy change of lattice energy by moving all of them to the left, and it again we will get the value of lattice energy with negative 903 kilojoules per mole. So we could have also question where they do not provide all information in the question, and they require us to get the values or the data from data booklet. So let's move into this question. It is from May-June 2007, paper 4, question 1. So after reading this question, we could actually see only 3 informations or 3 values are given here. So from here we could actually see the first ionization energy and second ionization energy for zinc, it's not given, and we do not have atomization of chlorine as well. So all of this we could actually get it from data booklet. So where from data booklet we can get ionization energy. And we can actually calculate atomization of chlorine with the bond energy from data booklet. So where we can have the relationship where atomization energy is equals to bond energy divided by 2. Let's construct the Born-Haber cycle in order to find lattice energy for zinc chloride. So we will start with the enthalpy chain of formation for zinc chloride. So it starts with the element, which is Zn solid plus Cl2 gas. So it'll be all the way down to zinc chloride solid with the value of -415. And the very first step to go, we'll go for atomization for zinc to the zinc solid into zinc gas, and the chlorine remain unchanged with the enthalpy of positive 131. So next step to go, it will be ionization energy to turn Zn gas into Zn2 plus gas by removal of 2 moles of electrons, and this involves first and second ionization energy of zinc. So we could actually make use of one level for these two energy to go. So where it is first ionization energy of zinc involving 908 kilojoules plus second ionization energy of zinc, which is 1730. And now here chlorine remain unchanged. So we have done with zinc by turning it into ions, and next to go we got to atomize chlorine. So for atomization of chlorine, so we got to turn this Cl2 gas into 2 Cl gas. So this is to form 2 moles of gaseous atom. So therefore, the atomization energy got to times 2, because there is 2 moles of gaseous atom it's formed. So here we will have to involve this relationship where we will have atomization equals to bond energy divided by 2. So we could actually get the bond energy of Cl2 in data booklet. And the value that we could get is actually 244. So bond energy divided by 2, this is the atomization of chlorine, and we have to multiply this value by 2 because there is 2 moles of chlorine gas atom is formed. So done with atomization of chlorine, the next to go, the arrow got to point down because it would be the first electron affinity of chlorine, where it is an exothermic reaction, and the value given here it's -349. It is to turn 2 Cl gas into 2 Cl minus gas. So again, these are the ions needed to form 1 mole of ionic solid in lattice energy. So the arrow will be all the way down to have lattice energy in an exothermic reaction. So after completed the energy cycle, where we have Born-Haber cycle here, so we have to go into the calculation to get lattice energy. So where we have the enthalpy change of formation with -415, where it is equals to all of this process to have ZnCl2 solid. So we're going to sum them up. Where they cancel off. So at the end, we will have plus lattice energy. So with the calculation, we'll get lattice energy of zinc chloride equals to negative 2730 kilojoule per mole.
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.